All right, recording is rolling. Here, right off. Let me try this Doppler ball again with this piezo because I had a little trouble with that yesterday. So, give you guys a better example of this. All right, so you guys see that single tone? Yeah, it's working better today. You guys hear tone rising and falling? All right. So that has to do with relative motion. All right, so pull that thing apart. Ooh, let me dig that up real fast. Where was? Here we go. All right. So what you guys just heard was this right here. There's some observed frequency that's different than the source frequency, right? Due to this relative motion. This is what I'm spending today in my other classes doing. I've got all these Doppler puzzles. Now, you guys, I'm not going to spend a ton of time on this because AP is not going to ask about that. But good to know about how that works. There's also a light version of Doppler effect. That's how, say, like astronomers know that the universe is expanding. A whole bit. So about that. Yeah, hey, maybe if you teach physics one day, then this could be good puzzles to throw at your students. All right. All right. So yesterday, I let you guys work pretty independently on those textbook puzzles. Now, you guys were pointing out to me, there actually was one that the solution didn't make it textbook. So kind of long story behind that. It was number 19, the one with the bananas. I don't know if you guys got the bananas and scale and said, what's the mass of the bananas? Right. Yeah, because when I was trying to solve this a few years ago, I was having a heck of a time solving this. So here, I have two different methods how to solve it. And of course, they both lead to the same answer. Right. So question was like this. There's a bunch of bananas in a scale, and you were given, I think, the spring constant and the time period to oscillate. And the question was, what's the mass of the bananas? Okay. And so I got a method one and method two here. Now, method one, I'm using conservation of energy. Oh, by the way, your guys's AP classroom puzzles that are due on Monday, right? The method I'm going to show you right now pops up. It's pretty handy for some of these puzzles, right? So let's do conservation of energy. Now, this is kind of a fudged version of this because if this is a vertically hanging spring, these bananas are changing height. So when I was first trying to solve this a few years ago, I was saying, well, wouldn't you have to consider gravitational potential energy? And notice I don't actually have any kind of MGH in here, right? Right. I was trying to solve it, and I was getting it was getting really complicated. And I was getting wacky answers that didn't make any sense, right? But the reason this is okay is because this is actually solving an equivalent similar puzzle, which is what if you take this whole thing and you just turn it horizontal, right? And you put this on an air hockey table. So there's no friction, but the gravity field definitely does not matter. And the motion is identical. And that's actually why it's okay to solve it with this method, even though I didn't consider gravitational potential energy. Okay. So I'm actually solving the horizontal version of this because it's identical motion. Okay. So I got 1/2 mv max square. Oh, I think they told you, well, they gave you enough information. I think they told you the maximum speed too of the bananas going through the center, right? Through the equilibrium point. Okay. Now, here's just a little detailed thing about the equilibrium point vertical is where the weight down and the spring force up cancel out, right? So the spring is stretched a little bit, but it is an equilibrium point. Versus the horizontal version is where the spring is completely unstretched at all, right? Right. So, but again, with this method, mathematically, it works out the same. Just a little details to think about. That's a little different, right? Right. And then they told you the amplitude, so 1/2 kx squared. Hey, that's like energy stored in the spring. Yes, because it's an energy setup. Right. So anyway, you can pop in all the values and solve for the one unknown, which is the mass, in this case, the bananas. Right. So you can solve it that way. Right. Right. Method two to solve this is you could think about these graphs. You guys remember these oscillatory graphs? Okay. It's also, this poster is also pretty handy for your guys' AP puzzles. And, like all the gold banner posters, you guys know could definitely help you out on this set of AP classroom questions and also your quiz questions coming this weekend, right? Right. Like over the years, like every main type of puzzle that I thought I could put into a poster is on a poster right now, right? Right. So if you think about this oscillating motion, and let's see, they want them mass of bananas. They told you V max. Now they told you V max. I'm thinking more along the lines of like this one right here. Something to do with velocity, right? You're trying to maximize out the velocity, right? So maybe like let's hit these points like this, right? And guys, sign of anything maxes out at what? 1. Yeah, this could be as big as 1 and as small as -1. Sign of it. You can put any crazy combination of whatever inside that sign. It can only go up to 1 and down to -1, right? So that would represent some kind of maximal value, right? So it's really this A times omega. and this omega is 2 pi f, and f, ooh, guys, what does f stand for? Frequency, which is 1 over the time period. Yeah, yeah, which is 1 over here. If you have one complete oscillation, isn't that, I'm showing one time period right there, one complete S shape, or you could go crest to crest, that's okay too, or trough to trough for that matter. It's all the same time period, right? Okay, so if you, right, so this is 2 pi times 1 over t, right, which could fit in here, and then times the amplitude, which is the maximal motion, right? Right, so here, so right, so we only got so much class time. Flashing this up here. I did scan this and I posted this to Google Classroom yesterday. Right, so if you want to get a closer look at that, but you guys see the end result is it leads you to the same answer. Okay, so you guys get that, right? And both of these methods are going to be, again, like I said, really handy for solving the AP Classroom puzzles this weekend. Right. All right. Actually, let's hit one of those because here, I'll help you out on one. I was looking at number 8, especially thinking, okay, you guys definitely could solve this, but it's one of those extra conceptual thoughts here. Right? Number 8, I think, looks something kind of like this. They say you got this block. Right? The spring is compressed at this moment. I think they never explicitly mention that, but you can sort of figure that out because they say it goes from this mark to like this mark here, maximum. Right? And they gave you the values, so like some number here and some number here. Right? And could you guys see that it would be oscillating between those two values? Right? You guys, if it's oscillating between those two values, where do you think that the equilibrium point is? Right in the middle. Yeah, that would be the equilibrium point right there. I'll call it a X equilibrium, right? And ooh, the spring would have to be completely unstretched and uncompressed at that point, wouldn't it? Right? And that's how you know that it was originally compressed. When you let it go, even though they never mentioned the word compressed, right? Right, guys, right. And they say, what's the speed of the block at this point? Bam, right here, right? Well, I guess when the block gets like right here, what's the speed of the block? Right? What guys would have the same speed going to the right as it would going to the left? Yeah. And I'm really helping you guys out with this one. Do you guys think you could sort of set up a conservation of energy, kind of like I did right here, and solve it that way? Right? Maybe you could solve it with this other method too. There might be a roundabout way, but let's set up a conservation of energy. Sum of energy at let's say either one of these maximum points where all the energy is in the spring. It could be either one. You think either way, right? Is equal to the sum of the energy at this special point right here. Call this point A and call this point B. Okay, so here's point A right there. There's point B right there. So this could be point A and this could be point B. Okay, so, right. So let's hit at point A. Could you call that all the energy is where at point A? In the spring. So what's the formula for that? 1/2 kx squared. Yeah. Now I'm going to change the x to a capital A for amplitude. Right. That's something you'll commonly see. Don't forget to, of course, square it. Right. Do you guys see what the amplitude is according to? Well, I don't have any numbers on this, but can you guys see graphically what the amplitude would be? Okay. You guys see it'd be this distance right here. Bam. I'll label that A for amplitude. Okay. No, well, okay. Stuff on the fly, but you guys get that, right? Right. That'd be amplitude. Okay. Yeah. Now, when it gets to this point B right here, let's say I call this distance x sub b. Okay. Well, the spring is stretched by that much, so some of the energy is there. Okay. So could that be 1/2 k x sub b squared? Okay. But that's not all of it. The block is also in motion, and so I also have to say plus what? Yeah, 1/2 mv squared is kinetic energy. There you go. Okay. And the question was, what's the speed of the block v? Okay. As long as you were given everything else, or you're able to find out everything else, right? Like they probably gave you the spring constant, and you can sort of figure out what the amplitude is. They told you x, right? Maybe they gave you the mass of the block. You could solve for v, right? Is that? Oh yeah.
Are they equidistant from the equilibrium point?
No, right? Because if they were, then the block would be way out here, and then it would have 0 speed because it'd be turning around. Right? But they're not asking for this point. They're asking for this point right here. Right? Just a little shorter way. Okay. Right. Yeah. So say for example, if this is like 10 centimeters. This would be 10 centimeters to get to the other extreme point, but this might only be like 7 centimeters out from the equilibrium. Something like that. I forget the numbers, but I guess it. Right. All right. So yeah, things you're looking for. Definitely know these oscillation graphs could help. Know these energy and conservation of energy. You could do energy methods. You guys know, of course, time period of a block on a spring, time period of a pendulum on a string. Guys, also remember Hooke's law. Guys, Hooke's law goes how? What is equal to what times what? F equals kx. That shows up too. Oh, yeah. Uh, the banana question. Um, okay, whether you use sine or cosine makes no difference. Right? Yeah, because sine or cosine are the same shape. They're just shifted apart, like one way or the other. Yeah. So whether you sine or cosine, right? Now, why did I go with sine? Because it matches this poster where if you start with position versus time being a cosine, then at time zero where you release it, it has this original displacement. So as soon as you let it go, you can start the stopwatch and it starts from some displaced value, right? And if that's true, then the rate change of cosine is sine, and the rate change of position is velocity. So the velocity graph would look something to do with the sign. Now it's a negative sign, it's like upside down. Right? And that's to say, also, when you release it from rest, it starts at rest, has zero velocity at time zero. Yeah. Right. So like that. Okay. All right. Let's get that. Yeah, but whether you have sine or cosine, either of those max out at one. So if you look at some maximum value. So that's why I bracketed all the stuff I said equals one, right? Because let's see, what's I doing here? Because that would correspond to a maximum speed. If they told you the maximum speed of the bananas, right? Then whether it's sine or cosine, it's gonna max up there, right? Right, you guys good? That's good. All right. All right. I hit all this agenda here. All right. So revisit Doppler, went over the solution. I gave you guys a few hints and things to look for your AP classroom questions. Okay. You guys all have your take-home quiz. Right, a few days to do this. All right. Oh, I checked my email. Do you guys remember our last few years? There's usually some resiliency lessons, right? So uh, they were changing things up this year. I heard we weren't supposed to do them, and now we just got word that we're going to do them on Tuesday, fifth period. So just that's there. Look for that. All right. All right. So you guys ready for FRQ time?